In this section, we will cover two common types of diagrams, histograms and bar charts. For our first exercise on this section, we will look at how to produce an histogram using Matplotlib. Based on the image of the Horsehead Nebulae that we used in the previous section, plot the pixel distribution using a histogram. We will proceed by using the histogram function hist of pyplot. We will discretize our histogram into 5 bins. If you look at the documentation of the hist function, you will note that the function is expecting a one-dimensional array. Therefore, we will apply the flat function of numpy to convert our 2D image into a one-dimensional array. We will add our axis labels and rotate by 45 degrees the TIX labels on the x-axis. And here is the result. We now have an histogram that includes 5 bins. By increasing the number of bins, we will have a finer and finer view of the distribution. For example, here we can see 2 examples using 10 and 1000 bins respectively. While this would go beyond this tutorial's vocation of being an introduction to the topic, I will invite you to think about what would be an optimal number of bins for an histogram. If interested, I invite you to look at the visualization module of AstroPy, which includes a few mechanisms to evaluate good bin sizes. You can find more information at the following link. Similarly, you can have a look at the scikit-learn module, a machine learning package, SciPy, or more widely into the literature. Next, let's fit the distribution. Here again, we will not go into all the details of finding the best fit, which would represent enough material for a full tutorial. We will instead look at some mechanisms provided by SciPy to fit a distribution. From there, you'll be able to continue your search for optimal methods. To fit the distribution, we will use the function curveFit of the optimize module of SciPy. The curveFit requires a few parameters, from which the first parameter is a function used to describe the model to be fitted. Based on the histogram we got earlier, we can think that our distribution is bimodal, as there were 2 peaks, likely related to the noise and the signal pixels in the image, respectively. Furthermore, we will assume that the distribution is Gaussian, a normal distribution. To represent our model of a bimodal distribution, we will use a Gaussian mixture model. Starting from these assumptions, we can define 2 functions. First, we will define our Gaussian model using the well-known formula. The function will take as parameters x, a value, mu, the mean, sigma, the standard deviation, and a, the height of the curve's peak. Second, we will define our bimodal distribution as being the sum of 2 Gaussians. We will first plot the original distribution using 1000 bins and save the components of the histogram into variables. Y is the values of the histogram bins. X is the edges of the bins with length n bins plus 1. The last parameter is the silent list of individual patches used to create the histogram, which we will not use. Looking back at the parameters of curveFit, we note that the second and third arguments are related to the independent variable where the data is measured and the dependent data, respectively. Therefore, we set our x value for the fit as a central value of our distribution. Finally, curveFit asks us to provide some initial guess as the 4th parameter. Therefore, we will set the guesses by defining an array of expected values by looking at the distribution. These values will fill the last 6 parameters of the bimodal function that we defined. Running these lines will return us the parameters of the fitted model, along with a covariance matrix, which we can use to get some statistics about the validity of our model. We will now overlay the model as a solid line onto the histogram. And here is the result. If you are interested in the parameters themselves, you can easily plot them using pandas. For the last type of diagram, we will produce a bar chart. In this exercise, create a bar chart with the data presented below. Include error bars and add a legend. The data below represents trial data, where one group used some medicine and another used a placebo. We will use the mean for the height of the bar and the standard deviation for the error bar. To set the bars on the x-axis, we will generate an array using the arange function of NumPy, using n bins, where n is equal to 5. We can also set the width of the bar to be a specific value. This is optional. Now, we plot the bars for each group. If you had a large number of groups, you could, for instance, automate this generation using the for loop. Finally, we will set our usual labels and add the legend. Here is our bar chart.